Yeah. Like you literally just, they gave you honors, so you just do all the time. And you're like, I'm done. Yeah, it was evenly.
So I think we'll finish 12.3 first and then
First time.
talk about the exam and any homework questions you might have. So in 12.3 we were looking at the r equals cosine theta, determining where the tangent lines are horizontal and vertical. And remember here in polar, the equation of, or that equation there, r cosine theta, describes a circle that's been shifted to the right. Because we want to think of this as 2 times 1/2 cosine theta. So there our a is 1/2. The center's been shifted over to the right 1/2, and the radius is 1/2. So what we did was we parameterized x and y. Since y was r theta, r sine theta, we just put in our r as cosine times sine, x is cosine times r. They gave us cosine squared. We found both of the derivatives for the vertical tangent line when the denominator is equal to 0. So that would be our dx over d theta. We did figure that one out. Talked about some of those points are actually the same point. And then for our horizontal tangent line, I think we sort of got to the point where we were saying cosine squared minus sine squared is 0, and we're trying to solve for theta there. So what do we do about solving cosine squared minus sine squared equal to 0? Do we remember an identity for that? So we can't really solve it as is. Or maybe we could, but identity is super helpful here.
Cosine of 2 times theta?
Yeah, it's cosine of 2 theta. So cosine squared minus sine squared is cosine 2 theta. And we solved a similar equation prior. So we said that's when theta is pi over 4, 3 pi over 4, so forth. So again, we have our theta values for which the circle has a horizontal tangent, and we want to know what the points are. So all we're going to do, like we did over here, is we're going to take these theta values and put that into the original function r. So theta equals pi over 4 into our cosine theta. That gives us the point 1 over root 2 comma pi over 4. Oh, well, I guess we'll do that. So, I would at least write down a few of these, and then you can compare, are we talking about the same points, or are they all giving me different points? So that's r equals to cosine of 3 pi over 4. So it's negative 1 over root 2. And maybe just we'll look at the 5 pi over 4 since we wrote that down as well. So that's also negative 1 over root 2, comma 5 pi over 4. And then we could keep going. Let's just look at what these points represent. You know, knowing that we're dealing with a circle, we wouldn't expect more than 2 points, right? There's not 3 points where the circle has horizontal tangents. So do we, with the 1 over root 2 pi over 4 compared to the negative 1 over root 2 3 pi over 4, are those the same points? Or are they different? So if I went over, my radius is 1 over root 2, and then I rotate pi over 4, that puts me up here, first quadrant. If I go out in the other direction, 1 over root 2, and I rotate 3 pi over 4, yeah, negative 1 over root 2, 3 pi over 4 puts me over here, right? So those are different points. How about the negative 1/2 5 pi over 4, or negative 1 over root 2 5 pi over 4? Negative 1 over root 2, and then 5 pi over 4 puts me here. So that's the same point. So knowing that we're dealing with a circle and we have 2 distinct points, that's really all we need. You don't need to keep going, because all of the other points that you write out are just going to be these 2 points in a different form. So our horizontal tangent occur at an r of 1 over root 2 theta pi over 4 and a negative 1 over root 2 3 pi over 4. And we'll go ahead and write our 2 points down for this one too. We had an r of 1, a theta of 0, and an r of 0, the theta was pi over 2 for a vertical tangent. And so in terms of our polar graph here, our polar coordinates, we also have the location of these 2, which are our horizontal tangents. Do y'all have any questions on that? Okay, we're going to skip the next example. It's rather involved. There wasn't anything like that in your homework, so since we're kind of pressed for time, we're going to move on to integration in polar coordinates. And then the idea of integration in polar coordinates doesn't depend on rectangles anymore, because we're gonna still slice up the region and sum up all those infinitesimal areas infinitely. But now what we're generating here is when we're coming from the pole out in wherever direction, wherever our region is at, and we're creating these maybe here, if we look at this, this is a circular sector. So if we just look at this thing right here, we're going to say what's the area of that sector, and add up all of the areas of the other sectors. So we're not dealing with rectangles anymore, we're dealing with sectors. So the area of the kth slice here comes from the area. Does anybody remember the formula for the area of a sector? You can probably get it from this right here, but area of a circular sector.
Radius times angle.
Yeah, the radius times the angle. It's actually the radius squared times the angle divided by 2. So that's the area of a circular sector, radius r. But we know again in 12.3 we're thinking of these polar, this polar region, I guess, or situation where r is a function of theta. So that's where the f of theta comes in. So f of theta squared is our r squared. The theta is actually all these little, d thetas here that we sum up, and then there's that 1/2. So that's really all we have to do is just infinitely sum all of those, the area of all of those sectors, just very, very analogous to Riemann sums. And so what we get is the formula for the, or how to integrate in polar coordinates. So we've got the 1/2, our radius squared, d theta. This is a more generic version. The version that would be applied to something like this is from alpha to beta. And this would just be our 1/2 times f of theta squared. The one presented in the definition is for a more generic setting, like when we have overlap between, maybe we want to know what the area is that's common to both of these circles. And if it were like, maybe it's centered like here or something, then our rays would go from here to here, like this. So you've got to think about what part of the area that you want to describe and what part of your rays emanating from the origin will actually sweep that out. So really what we want to focus on are these rays right here, or these circular sectors right here. Because as those sweep from this intersection to this intersection, we're only going to account for that area that's common to those circles. So the f, the f of theta minus the g of theta could be something like this, or maybe you want to think about f of theta as the outer or the outside, the one furthest from the pole, minus the inner, which would be our g. So like in a situation like this, if we didn't do the outer minus the inner, we wouldn't sweep out that red area. If we just did the outer of that circle, then what we would, from wherever to wherever, we would be determining this area here. Does that make sense? Can everybody sort of visualize that? And so of course the intersection, this is our alpha, this is our beta. Remember, these are the alpha and the beta are theta values. So, sometimes you have to find those. What are those points of intersection? And it's not an easy thing to do, because even if you look at a graph, the graph is a static thing. They may not intersect at the same time, so to speak. So you sort of have these simultaneous points of intersection and these non-simultaneous points of intersection. Fortunately, I don't believe we deal with some of those more difficult cases, but things can get difficult in this kind of setting for sure. So let's look at a couple of examples then. So we're going to make a sketch and find the area of the region inside the circle, r equals to 8 sine theta. So as far as that circle is concerned, what are the details for that circle? Meaning, what is the center and what is the radius of that circle? 0, 4. Do y'all agree with that? Center's at 0, 4. Radius of 4. Since it's sine, it affects the up and down, vertical dimension. So we could certainly sketch that by hand. I'm not going to try that. It's very difficult. Let's just graph it here and put it in our notes. So, I mean, naturally, like, integrating this wouldn't be the most efficient way to find the area. Now that we know it's a circle of radius 4, it's a lot easier to find the area pi r squared. We'll just use the pi r squared as a check just to see that this actually does work out. So we want the area inside the circle. So we're thinking of our our sectors doing this kind of thing throughout as theta varies from somewhere to somewhere, right? We're sweeping all of that out with I guess we're really not. We're those are all little tiny rays. They're circular sectors. So when we set this up, when we say the area is equal to 1/2 the integral, just write the formula here, of f of theta squared d theta. Most of the time the issue isn't figuring out what function you integrate. A lot of times the issue is figuring out what are the bounds of integration. In other words, what are the values of theta from which we start and stop. So I guess there's a couple of ways to look at it. The symmetry that's present in these figures, especially in like polar coordinates, can be really, really helpful. So sure, we could aim for just with in one fell swoop getting the area of that circle. Or we could say, since there's symmetry here, we could look at half of the area and then just double it. So how do we determine what theta ranges from for our bounds of integration? You can see maybe like as theta were 0 right here, and then for half the circle, I think it's easier to see theta is 0, and then all of our sectors are ranging from 0 to pi over 2, right? And so we would get half of that circle if we did that. If we range from, theta range from 0 all the way to pi, and then you can kind of envision that sweeping out that full circle. But a surefire way to see that is this point here in the polar situation or the polar setting is what we call it the pole, but what is the pole when what? Not well, when r is equal to 0, yeah. So at that point r equals to 0, we can say, well, when does the circle, when does 8 sine equal to 0? In other words, when does this figure intersect the pole. And that happens at 0, at pi, at 2 pi, and so forth. So if we go from 0 to pi, again, that's our theta starting out right here, and then going all the way throughout to here. And that would give us the region inside that circle. Do y'all agree with that? Does that make sense? Are there any questions? We wouldn't want to go to 2 pi because if theta ranged from 0 to 2 pi, then we're getting all of this stuff out here too, and there's no area out in that or below the x-axis, I guess. So we wouldn't want to go through all the way through 2 pi. So that's the area inside the circle. And I mean, we could integrate that, or we could say that, half that region from 0 to pi over 2, and then we can double everything. So it's totally up to you. It's all the same. Everybody okay with the setup? I think the integration should be not too terrible with most of these. So then, sine squared is something that we've integrated so often. So we have 1/2 as the antiderivative of sine squared, 1/2 theta, minus 1/4 sine of 2 theta from 0 to pi over 2. So pi over 2, let's see, yeah, let me just check that, that's 1/2, 1 minus cosine of 2. Okay, yeah, so pi over 2 in for theta, we've got pi over 4 minus the sine of pi, or minus 1/4 sine of pi, so that's 0. Minus 0. We have 64 pi over 4, which is 16 pi. And again, our check was that it was just a circle radius 4. Pi r squared. Does anyone have any questions?
Just really fast, how'd you get from sine squared to the integral of it?
Yeah, so we all remember how to integrate sine squared or cosine squared? Yeah, probably. That came up a lot in trig substitution.
Oh, it's 1 minus cosine squared.
Well, yeah, it's we rewrite sine is 1/2, 1 minus cosine 2 theta, and for cosine squared it was just plus here instead of minus. Yeah, I mean sine and cosine squared are so common. I would just remember what they are. Any other questions on that one? Okay. All right, so then find the area common to the circle r equals 1 and the cardioid r equals 1 plus cosine. So rather than spending time trying to graph these things on the final, for one of these types of questions, I will give you the graph. I'm just going to read. So the area that is common to is what we want to look at. So this is the area that we want to describe. So a lot of times you can make things easier, not only with symmetry, but with, in this instance, if we want to find that area that's common to, well, most of that area is coming from what? Yeah, most of that area is half of that circle, right? So if we find all of that area and all of this area, then we have our answer. So let's do the, let's just do it this way and say that it's the area of the blue region is just half the area of that circle. And the blue circle is a radius 1. So it's just half pi. So then what we have to determine is what is the area here in red from the cardioid. So again, you've got to envision these rays from the pole here. Here's the pole. Different color. To describe this area, our rays have to go from there to there, which would be from a theta value of what to what? Pi over 2 to pi. Yeah, and so we might you might then say, well, is that, does that really, that sort of cusp portion of that cardioid, is that really happening when theta is pi? And the way to check that is that part of the cusp or that part of the cardioid is at the pole. So we would just take like we did in the last one, we just take the cardioid and determine when it intersects the pole. So when is that 0, when cosine is -1, when is cosine -1, at pi, at 3 pi, so forth. So if we say, all right, then, well, that area of that region is 1/2 the integral from pi over 2 to pi on this function squared. Is that going to do it? Yeah, we have to multiply that by 2. Again, we can use symmetry, or we can try to go, we can set up another integral and say from pi to 3 pi over 2 and integrate the very same thing. I don't know why you would do that. It's highly inefficient, but you certainly could do that. So we need 2 of these. Because that's just from pi over 2 to pi is the top half, if you will.
You could just do that in one integral too, right? From pi over 2 to 3 pi over 2.
Yeah, from pi over 2 to 3 pi over 2. But most of the time you can use symmetry with these. It's gonna yield a simpler integral, for sure. All right, so the red area, the total red area then is just this. We're going to have to expand the 1 plus cosine. But that's pretty much it. We can integrate each term. So is everyone okay with the setup and the bounds and such? Okay, so then we expand the function 1 plus cosine theta. Integrate each term. We have, let's see, 1 plus cosine squared, 2 times pi. Okay. Yeah, so then this one is going to be 1/2 theta plus 1/4 sine 2 theta for cosine squared, and then we've got 2 sine theta from pi over 2 to pi. Call that 3/2 theta if you want. Yeah, so it's just a bunch of stuff here. 3 pi over 2, 0, 0. Just write it out, I guess. Pi, sine pi, yeah, so those are 0, minus 3 pi over 4. Zero and 2. Wait, yeah. Minus all this, so that's plus 2. We have, what do we have? 6 pi over 4 minus 3 pi over 4. 3 pi over 4 minus 2. And again, that area is for the just that portion on the cardioid. We still have to add this area to the area for the half of the circle. So the area, the total area common to those figures, 5 pi over 4 minus 2. Do you all have questions?
If this were on the test, is it okay to use the pi r squared method of finding the area of the circle and then doing the integral for the cardioid, or would you expect to see the integral for both parts?
No, I don't think I really have a preference. Yeah, I think the one on the final is set up to where you have to integrate somehow. So yeah, it doesn't, I don't care. Right. Yeah. I mean, and you know, this stuff is really involved, and you can do a lot with it. We just don't have a lot of time, so we're just highlighting some things. So you can work in polar coordinates. You can take derivatives in polar coordinates. You can integrate in polar coordinates, and you can find other stuff. The other thing we're going to look at is arc length in polar coordinates. So we've got a continuous function. A continuous derivative, rather, on the interval. Arc length is defined as follows. And if, you know, this is for the curve that's defined from A to B, or alpha to beta, rather. Sometimes you're not given that, so you kind of have to either, you know, look at what the graph is and determine kind of, you know, where does it start and stop, so to speak, or you know, how many thetas does it take to graph that entire figure? Not always are you given that interval, but it is the square root of r squared plus r prime squared, or f of theta squared, f prime of theta squared. So the arc length of the cardioid, that was in our last one. We'll go ahead and graph this one too, just so we can reference it. So we've got f prime, or sorry, we have f of theta squared. We need f prime. So what is f prime of theta? Yeah, negative sine theta. I'm gonna run out of room here. So f of theta squared, just like in that last one. And f prime squared. So we've got to add those two together on the left, or sorry, on the right, and then we have to take the square root of that. But we also need to know the bounds, alpha and beta. So what would our bounds be? 0 to pi? What do y'all think? If you multiply it by 2, yeah. So here's theta equals 0 to theta equals pi. Once theta is pi equal to pi, as we saw in that last one, then you're at that pole. So if we just went from here to here, we would have to double it. And I think this is going to be a lot more efficient for us if we use these bounds. Otherwise, we would have to do this. And as we'll see, the way this particular integrand simplifies, it's not that we couldn't do it, it would just be a little bit more difficult. All right, is everyone all right with the setup? Any questions on that? So then, so what can we do here? Is what? Okay, so that's going to be 1. And so we're still left integrating the square root of 2 plus 2 cosine theta. D theta. And I think we're going to stick with the first one we wrote down, 2 times the integral from 0 to pi. Yeah, so we could certainly factor out this 2 and then take out a root 2. And we're still left integrating square root of 1 plus cosine theta. Trying to think, we had a homework problem that was similar to that. Anybody remember how we would integrate that? Sorry, I don't remember what section it was from. I think actually what you had to integrate in one of your homeworks was the integral of the square root of 1, maybe 1 plus cosine 2 theta. Does that seem vaguely familiar to anyone? No? No, so it wouldn't be a trig sub. A U substitution in what way? Do what? Yeah, but then what's du in terms of? So you don't have that negative sign is the problem. Well, then you have a different function. What about this one here? Does that 1 plus cosine of 2 theta look like it came from something else? Remember this? So isn't 1 plus cosine of 2 theta the same thing as 2 times cosine squared? So if we put that in there, now we have root 2 times this integral.
You have the, you have 2 cosine of 2 theta there?
2 cosine theta? Yeah, 2 cosine squared theta.
Okay. On this one though, we've just got the 1, it's
Mhm.
not the 2 theta, so we have to adjust that.
We'd have to adjust that, right?
Yeah.
So but this is the key. This was from your homework. It might have been a minus where it was 2 sine squared. I don't quite remember. But the idea is that we're going to use the very same identity to help us integrate this. So we'll just write this out. So that's the kind of the identity that we're usually working with, but we don't want an expression for 1 plus cosine of 2 theta. We want one for 1 plus cosine of theta. So how do we adjust that? You just change the, yeah, and maybe it's weird to see the thetas here because we're trying to change it into theta, but let's just do it this way. Let's just call that x. So then to get here, we would just say, well, I want 1 plus cosine of something, not 2 times something, right? So then if you need to see it the way, in a direct way, you would say, all right, well, I'm going to let theta equal 2x. If theta is 2x, then what is x? Yeah, half theta. So that's our identity for the one we actually need. It's 2 cosine squared for the identity rather of just 1 plus cosine of theta. Let's try this again. There we go. Okay, that means we just have to half that angle. So that's how we're going to rewrite that expression under the radical. And so now this is where, if we were to stick with the original, the full arc length from 0 to 2 pi, this is when we would have issues, because we're going to say the square root of cosine squared is not, or cosine squared of theta over 2, it's not just cosine of theta over 2, it's the absolute value, depending on where cosine is positive and negative. But with the bounds from 0 to pi, we don't have to worry about that, because cosine of theta over 2 in the region 0 to pi would always be positive or 0. So again, we're just going to take that root 2 out. And simplify this. As the cosine of theta over 2. Cosine of theta over 2 has a period of what?
Pi.
Of what?
Pi.
Not pi. What? That would be for cosine of theta.
4 pi?
It's 4 pi. Since cosine of theta over 2 is larger than or equal to 0 for theta, we'll just make that note. But over here, cosine of, remember the period of cosine is 2 pi over this thing here. So 2 pi over 2, 2 pi over 1/2 rather gives us 4 pi. So if this is the graph of that stopping at 4 pi, this is pi, sorry, this is 2 pi, this is pi. So this is all cosine pi over 2. Clearly you can see that it's positive or 0 in between 0 and pi. If we were to use the original bounds from 0 to 2 pi, well then sometimes it's positive and sometimes it's negative. So then you've got to look at this graph and say, all right, well I split that up into two integrals from 0 to pi minus the integral from pi to 2 pi. Kind of like what we did when we were computing like distance traveled or something like that. So this region allows us to just take the square root without the absolute value. Okay, so what is the antiderivative then of cosine theta over 2? Huh?
2 sine theta.
2 sine theta
Theta.
over 2 from 0 to pi. And then that's our arc length. So you could imagine there's, like this one was, I don't think it was too bad, but some of these can get really terrible because you've got the function squared and its derivative squared underneath the square root. So you've got this sine of pi over 2 minus h. So you got a couple of those in your homework. Not one of those on the final. Okay. Do you all have any questions on that one? Well, that's the end. The end of Calc 2, you made it.
Allegedly.
I don't know, I hear some people say Calc 2 is harder than Calc 3, some people say Calc 3 is harder than Calc 2, so if you go on, let me know which one you thought was harder. So I know some of these are pretty vague, like the multiple choice. Those 12 multiple choice questions will be over everything, or could be over everything.
For like algebra.
Huh?
And they just be algebra problems. Just like 6x
Yeah, they have to be really hard,
equals
though.
9.
If it's algebra, it's going to be super hard. Find the inverse of the hyperbolic sine function. Yeah, so those multiple choices will embody everything, or could embody everything. They're not just going to be limited to new material or old material. It's kind of all of it.
That's scary.
Huh?
That's scary.
No, I mean, in theory, these are ones that you should be able to, you know, like, I don't know, something to the effect of what does this represent? You know, stuff like that. Is that a circle? Is that a hyperbola? Is that a circle centered here? Is it circle centered there? You know, just stuff that if you have exposure shouldn't be too thought provoking or cause you to think too much. That's kind of the idea, anyways. I know it's relative in my mind versus what's in your mind, but that's what it is. The set up and evaluate the integral to find the area between two curves, that was the first thing we did in 6.2. Disc washer and the shell, let me just write these sections here. This is 6.2. Disc washer was 6.3, and the shell method was in 6.4. Some of these I don't quite remember what their sections were. Evaluate a given integral by parts, partial fractions, or by trig substitution. I'm not going to tell you which one because I want you to know all three, just in case.
Maybe by parts. Sounds like a request.
Well,
It's so much easier.
no, I won't specify which one it is.
But you've already written it,
Yeah, I've already written it,
so you know.
so I know. That's right.
Which one?
All right, beat them up after.
There's one of those, there's two. You're given a series, determine if it converges or diverges. Oh, I did write an example for this one. This is kind of like on the last test where you're given a series. I say, you know, this particular series for x is this. Find like x squared minus 1 over 2x. So that's where you're composing something into a series and multiplying by a power of x.
Oh, okay.
Yeah, and I went ahead and worked that out.
So is that still going to be like one of the 4 or 5 or whatever that you've given us?
Yeah, that you should know. I mean, you can put the series stuff on your note card if you're worried about it.
Well, I didn't know if there was like a specific, because there's only one question of that. But on 11, whatever, you had said, hey, there's going to be, or 10, whatever, there's 4 or 5 that you need to know, like,
Oh, right.
yeah, 1 over 1 plus x, 1 over 1 minus x.
Uh-huh. E to the x.
E to the x, the cosine and the sine.
Sine, yeah.
So to just know those 5 again? Or
Yeah, I mean, and if you don't want to know them, just put them on your note card. But yeah,
if
I
you
think...
could narrow it down to less than those 5.
No. Find the tangent, slope of the tangent at a given point in polar coordinates. Parametric equation, you should be able to convert it to Cartesian. Find the derivative at a point and the slope of the tangent at a point. 12.1. And then 1 from 12.3, you're finding the area.
So we don't need to
That's the
study
final.
12.2.
Huh? That's it. Yeah, I mean, it's there's so much material. Some of it takes so much time. It's virtually impossible to test over everything.
Yeah.
Yeah.
How much 2 days?
How much is it worth? It's out of 100 points.
But like all the whole tests were out of 23, so is it more than all?
Like just the percentage of your total grade compared to the other tests? No, the final is worth. I know other professors do or instructors do finals where the finals are like 25% of your grade, but this final is the same as any other test because it's not 100% cumulative. So, do you want to take a break?
Or just take off.
Is all of it an appropriate answer, or is that kind of?
Is what?
I said, is all of it an appropriate answer, or?
Well, I don't know that it's inappropriate or appropriate. but
I mean, do you
do
want
have
to
limited
throw
time.
us, 6 of us in here, a bone for hanging out? for a while?
It's being recorded, so.
I mean, you can stop the recording. I mean, the recording will go on
I
for
always
the
wanted
rest of this
to
time.
like stop the recording and like write a bunch of complicated math, and then be like unpause it and say, and that's the meaning of life, and have the class go, oh, and everybody at home will be like, dude, what did I miss?
And that's how you get an A Calc, yes.
Yeah, I don't know that I have anything specific. I just had some various things written out, or examples written out for like area, disk washer, shell.
Yeah, sure. Might as well just refresh those old.
Integration by parts, trig sub. You know, I think a lot of this stuff would be really conducive to put on the note card, you know, because you already have to remember so much. And so, like, the things you can put on your note card is if, let me write one example down. So find the volume of the region R bound by square root of x and x squared when R is revolved about the x-axis. Using disk or washer. And then we could perhaps look at that same region with shells as well. But, you know, something you could put on your note card is, you know, you could even like draw out the scenarios here and say, like, you know, you have a region like this revolved about the x-axis. You know, you can draw generic things. This is your small r, this is your capital R, disk. You know, however you want to write it out, I guess. You know, and that translates to pi times the outer squared minus the inner squared. You know, like that's perfectly fine to have on your note card. Of course, that's not what we're dealing with a specific problem, but again, if that's f of x, you could say, all right, well, disk. Oh, sorry, this is, I mean, that's a washer, yeah. Disk is just pi r squared, or pi times f of x squared dx. You know, that's not a specific example, so that's perfectly fine. Oh, you know, and other stuff too, like from our work in you know, this arena, we said that the disk /washer. Our rectangles or our elements, our slices, whatever you call those things, are always perpendicular to the axis of revolution. You know, just writing stuff down that, you know, maybe I forgot. It's still kind of in my mind, but I don't want to remember. So all of that kind of stuff is acceptable on the note card, because it's not a specific example and it's not from chapter 12. So anyhow, we've got the region for R as the region bound by x squared and the square root of x.
Will you be giving us those kind of graphs too?
If the graphs are a little bit more involved, for basic ones like quadratics, square roots, stuff like that, probably not. I'm trying to remember what I did this over break and I forgot exactly what I put on the exam. So then we're going to say, all right, well, I'm going to revolve around the x-axis. That was given in the problem. So I'm revolving around the x-axis using disk and washers. My rectangles, slices, elements have to be perpendicular to the axis of revolution. So I know that when I look at these things, that all of those slices, cross sections, rectangles, whatever, they're all going to have a thickness dx, and then that tells me that my bounds, my function, need to be in terms of x. So I think that's a really important aspect of the shell and washers. On that first test, there was one page where it was the same region revolved around various things using various methods, and a lot of people lost a whole lot of points because they were just setting it up. I think this is what it would be. I promise if you draw the region out and know how to construct the rectangles, that it's going to tell you all you need to know.
So to find that, or to find the bounds, it would be 0 to the intersection of x squared and
Correct.
Right? So that would
Yeah.
just be setting those equal to each other, right?
Right.
Okay.
Because the region we're imagining like filling up, all of that. We've got an outer radius here and an inner radius because we've got this gap between the axis of revolution. But yeah, the x values, our rectangles, range from there to there. Okay, so solve that the way we solve square roots, particularly the issue here. We're going to square both sides. And then for these types of things, you've got to factor. If you don't factor, you're going to miss at least one solution, typically. So I think it's trivial to look at that and say, well, x to the fourth equals, and it may be a straightforward equation, but most people might end up just saying, oh, it's true when x is 0, and forget that it's also true when x is equal to 1. Sometimes the region can help. You should come up with, you should be able to determine 2 points of intersection, maybe not from the equation, but usually you can get them, all of them from here. So we just factor out an x. And see that the intersection points are when x is 0 and when x cubed equals 1, or when x is 1. So we know that's, of course, 0 and this is 1. Okay, so we've got this gap. We have all of those green rectangles from the red down to the axis of revolution. Those are going to be the outer radius, or radii, and from the inner function to the axis of revolution, or the lowercase, or the inner radius. So we have the volume as pi times the integral from 0 to 1. Our outer radius squared. Our outer radius, again, is we're just now measuring the height. The height of the outer radius will always be the top minus the bottom. So something else you can put on your note card here is top minus bottom. For dx, right minus left for dy. I mean, and I'll just write this out so it's like, you know, maybe totally clear, but there's the outer radius squared minus the inner radius squared. Be a little redundant, but, and it's with respect to x. So that should be straightforward for the integration. Bounds are pretty simple. Powers of x. So yeah, and so with that, what if we? Is everyone okay with that? So what if we said let's look at that same region. Let's look at the very same region, but revolve it around a different axis. So like R revolved about, let's say, y equals to -3. So the similar situation here, there's space between the actual region and the axis of revolution. So it's going to be a washer situation that we have here. But this time, since we're revolving it around this, our outer radius is now from this function all the way down to the axis of revolution. So that distance, again, is just the top minus the bottom. And so the outer radius in this particular kind of setting would be, I'll just call it, well, we're using capital R for the region, so I'll just say that the outer radius is still the top minus the bottom, but this time the bottom axis is different. So that's our square root minus the bottom is -3. So there's the outer radius this time. The inner radius, similar situation, top minus bottom, the bottom being -3, so x squared minus -3. It's a little bit more of a involved integral, but you know, as you might remember, with these, the setup is often the most difficult thing. Bounds still 0 to 1, pi times outer radius squared minus inner radius squared. So just remember that, like, if you're going to put the pi out front, that's totally fine. If you're going to leave it in, the pi is actually attached to both the big radius, outer radius, and the inner radius, right? This is the thing we have is something like that, and what we're actually finding is the area of the washer itself. So there's our outer radius. There's our inner radius, but all we're after is this area here. Each one of those rectangles or cross sections is sweeping out one of these things. And so the area of that, you take the area of the whole thing minus the area of the small circle. So just make sure you've got the pi in the right place. Outer radius squared minus the inner radius squared. So it's still powers of x, there's just more terms because you've got to square both of those now. You'll end up integrating those. That's, just powers of x right there. You integrate each piece from 0 to 1.
But you should still have just some stuff canceling out. I mean, the 9s will cancel out.
Yeah.
That's about it.
The 9s will, yep. The 9s will cancel out. Yeah, and so that's what happens when you change the axis of revolution if it's not the x or the y axis. You'll always have an additional number in there with your radius with the disk and washer method. So we could take that same region so R revolved about the x-axis still using the shell method. So this method, that when we use shells, the cross sections or the slices have to be parallel to the axis of revolution. And the shells have a different formula. Shells were 2 pi times the radius times the height, which was 2 pi times the integral. The radius here of each one of these shells, if we're going to revolve this around the x-axis, that's our shell, cylindrical shell. The radius of that shell is determined by the distance to your slice, the distance from your slice to the axis of revolution. That's the radius of the shell. The height of the shell in this view, from this viewpoint, is this dimension here. This is the height of the shell. So, it kind of depends. If we were to take that region and revolve it around the y-axis using shells, the radius, still the distance from the rectangle to the axis of revolution, and the height is the top minus the bottom because it's in a vertical direction. So the radius is just defined I guess whichever situation we're dealing with. But the radius was just x, and the height was given by f of x dx. I mean, that's the more basic one, of course. Or if we were integrating with respect to y, radius is y, height is g of y. We've got a little bit different of a situation for this one, but the main idea is that we're kind of aware of what scenario we're dealing with, and then we can sort of fine tune it based on this particular region.
But that R depends on if you're revolving it just around the x-axis or like y equals like -2 or wherever.
Yeah, if it's y equals -2.
Then that would be x plus 2.
Right,
Okay.
exactly. So notice our rectangles are running horizontally. All of these rectangles have thickness in the y direction, so we've got to integrate this with respect to y. The bounds need to be in terms of y. The function needs to be in terms of y. So we have this point, this x value is 1. We plug it into the square root of x or x squared to find out that it's 1, 1, because we need that y value. Our rectangles to fill this region up are going to range from 0 to 1. 0 y value and a 1 is a y value. So the volume here would be 2 pi times an integral from a y value of 0 to a y value of 1. What's the radius of all of our little horizontal elements, our rectangles? We don't have too much going on up there, but like if this were the rectangle I was focusing on, what's the height of that? In other words, what is that distance?
Why?
It's just y, isn't it? It's just some y value. If I told you that was a y value of 1/2, then that radius right there is 1/2. It's not 1/2, it's just whatever y is. Okay, so the radius here is just y. Again, if we were revolving this around the line x equals to -2, then our radius would be y plus, or sorry, y minus a -2, which is y plus 2. And then the height of each rectangle here, it's not just a single function, right? Because the height of our rectangles is defined as the right minus the left. So you've got this function in blue minus the function in red for the height of all of those. But since we're integrating with respect to y, they need to be in terms of y. Yeah, this is... Okay, so we don't want to say this, we want to say that x is y squared. So that's the left, and our right is the square root of y. So this is the radius, this gold y here. The height of each cylindrical shell is defined as the right minus the left. And so you just distribute the y, integrate powers of y again.
And that's revolved around the x-axis.
Correct. Shells are always parallel to the axis of revolution. Yeah, so does that spark any interest in something else you thought of? You want to look at?
Could we look at trig sub again?
Trig sub, yeah. just wrote one down or not. So let's evaluate the integral of 1 over 16 minus x squared to the 3/2. So, another thing, since we're talking about another thing you could put on your note card is if it's, a squared minus x squared, I should let a equal to whatever, those three different ones we had, you could write that out. So what we did with these though is the textbook said just, leave it like this. This is your a squared, so a is 4, right? We were factoring these things out, so it was 1 minus x squared. So then we would write this as we would factor that 16 out. I mean, you don't have to do it this way, but this is how we did it. All of that still to the 3/2. So we can take out, go over here, we can take out the 1 over 16 to the 3/2 as a constant. We're going to rewrite x squared over 16 as x over 4 quantity squared. And then all of that's to the 3/2. So in the instance where we had 1 minus a square, what did we substitute? Sine, yeah. You could substitute cosine as well, but we're thinking about the Pythagorean identities since 1 minus sine or cosine squared just gives us another square like sine squared or cosine squared. That's kind of how those subs were based off, or what they were based off of. So we're going to say x over 4 is sine theta. And we've got to account for the differential. So we've got to take the derivative of x with respect to theta. Which is 4 cosine theta d theta. And the one of the, I guess, most obvious benefits of trig substitution is being able to take care of a square root of a sum or difference of squares. And that's kind of what we have. Even though it's to the 3rd power, it's kind of irrelevant. We're still taking the square root of a difference of squares. All right, so substituting in, what is this constant? 4 cubed, 64. Our dx is now 4 cosine theta d theta. We've got the quantity now 1 minus sine theta squared. And all of it's still to the 3/2. That's quantity now is just cosine squared to the 3/2. And then you get guess we could have divided these 4s into 64s, but remember the cosine squared to the 3/2 is really the square root of cosine squared, all to the third. That's what that is. So you just have cosine cubed on the bottom. Constant with the 4 now, we're going to write that as, just write that as 1/16. One of the cosines cancels, integral of 1 over cosine squared theta with respect to theta. We're going to call that secant squared theta. And the integral antiderivative secant squared. Should know that. Tangent. And you know, this is where like the other trig functions, like what's the antiderivative of secant? Or the antiderivative of tangent? That's where oftentimes you see those was with trig substitution. So, you know, those the other trig functions, secant, tangent, cotangent, and cosecant. You should know those antiderivatives. Something you can put on your note card. Remember these were the weird ones that involved natural log absolute value, secant theta plus tangent theta, you know, those kinds of things. Sine over cosine.
You have to remember where, because I remember that in our notes that we have. I
Yeah,
can
that
just
was-
look at them right now.
Should have been in the, where the, 8 something.
I think 7.3.
It's in another place.
Yeah, 7.3 or 7.4 is where those were.
These are, I think, in syllables supposed to grab these.
So you've got the antiderivative in terms of theta, then that's when you go back to your substitution and you say that the theta represented, the sine of theta, our substitution, sine of that angle was x over 4, so the opposite over the hypotenuse. And then we can find the other side of this triangle as that. So we can actually now determine what the tangent of that angle is. Tangent of theta is this. And that's pretty much it. So don't forget to resubstitute for theta. A lot of people will forget, because I mean, you know, it's kind of a lengthy process. By the time you get there, you're tired. You forget. Don't forget.
Would you want it more broken down than that, or just that?
No, that's fine.
Okay.
Yeah. I think on the first exam, I was, some of the ones that involve like the ln of stuff, I was given an extra point if you could write it without like the ln of a difference or something like that. But yeah, that's fine. I won't. There's not any extra credit on the final, so.
Only 50 points for spelling your name correctly.
Yeah, I wish. I wish. I'm not a. I don't know. I'm not a huge fan of the testing metric, but so it is. Anything else you want to look at?
Let's do a fraction.
Partial fraction. All right, let's see if I have one. Partial fractions were in 7.5. No. 8.5. Which one shall we do?
Are we gonna need to do long division?
Could be, yeah, could be a possibility. Wouldn't rule anything out.
Really not giving up any hints on.
No. I don't, yeah, there's so many. My God. 50, 64 of these. I don't know how long this would take, number 40. It doesn't look that bad, but until we start working it, we won't know. So for these, you had to remember, like, once you've had the denominator factored, what type of factors are you dealing with? Because the type of factors in the denominator determined whether you had an a or an ax plus b, ax plus b squared, whatever, in the top to actually solve for this. So we've got this is a simple linear. This is a repeated linear. So with this, we would say that the entire thing, entire integrand, is equal to these partial fractions. We've got a simple linear, so that's the case where we just had a coefficient like a. And for the repeated linears, you just want to account for all of them, I guess. I don't know how to say that. So we have b over just an x plus 2 and a c over x plus 2 squared.
And if it was cubed, then it would also be like add on a cubed and so
Yeah,
forth.
yeah, like a d over x plus 2 squared.
And then what about if you have an x squared in the, like x squared plus 5 or something?
Yeah, so like the whatever the stuff over x squared plus 5,
Yeah.
just like by itself, then you say that's equal to ax plus b over x squared plus 5. Yeah. And then if it were stuff over x squared plus 5 squared, then you do the same thing you do with the ax plus b, similar to the repeated, yeah.
CX plus D.
Yeah. Plus cx plus d over x squared plus 5 squared. And so then we have to solve this equation here for a, b, and c, which we're just multiplying through by this common denominator here on the left. So we have that 16x squared is equal to our a times x plus 2 squared plus b times x minus 6 times x minus 2 plus c times x minus 6.
X plus 2.
Yeah, x plus 2. That one. Okay. And so from here, the shortcut method might work. It's worth trying. The shortcut method, you could at least solve for one variable and perhaps not have to have a system of equations you have to solve. So we're going to say let x equal -2. And so the a and the b terms will go away. And then what that'll give us is we've got our 16 times -2 squared equals to c times the quantity -2 minus 6. So we could solve for c with this. Yeah, 64 minus 8c. Divide. Solve for c. So we've got c to be -8. Okay, and then we'll let x be +6. So we've got our x 16 times 6 squared equals, the b and c go away. We have a times, let's write it out, a times 6 plus 2 squared. So we've got 864a times a.
576.
576. Let's see if it's. Oh, did you already simplify it?
Yeah.
Okay. So 576 here,
576.
and that's divided by 64. What does that give us? 9. So we've got A and C. Unfortunately, B had both of those factors. So a little bit more work is required to find B. But let's go ahead and fill out A up here as 9. And so since we didn't get all of them, then you've got to kind of multiply this stuff out, equate coefficients, because you need a system of equations, preferably one that has B by itself would be ideal, but any other ones that involved A or B or C or B could find that for us. So finding B. So you have to multiply all this stuff out and equate coefficients. We've got an ax squared plus 4 ax plus 4a. What do we have here? We've got a bx squared minus 12b. We've got a -6, -4bx, and then cx minus 6. C. All right, so then we've got our x squared coefficients. So that'll do it for us. We'll be able to solve for b with just that one. So we've got our 16 is equal to a plus b. Just from that, we know a is 9. Let me write this here. Okay, which tells us b is 7. Really not any need to go any further with our equation. So b is 7. Nine, 7, and 8. So the original integral then is broken down into those components or those parts. That's equal to 9 over x minus 6 plus 7 over x plus 2. I think c was -8. Yeah, c was -8. Minus 8 over x plus 2 squared. A lot of those are log form. A lot of these come out to be, some of them come out to be like an inverse tangent. And some of them are U substitutions. So the 9 over x minus 6 is in log form, so that's 9 natural log absolute value x minus 6. Same thing here. Minus 8. 1 over x plus 2 squared, antiderivative of that. That one would be a U substitution. So that's what we get. We get our -8 times -1. We've got our U to the -1, or 1 over U plus 2, or x plus 2, sorry. Never mind, I'll leave it. So I wouldn't say they would be any more difficult than that on the final if they show up. Yeah, prepare for everything, right? So if you don't have enough to remember.
Jack of all trades, master of none.
Yeah. Yeah. I still feel that way. So, you're good. Got about 10 minutes, so I still want to look at it.
How'd you get the -1, U to the -1 again from that?
Power rule, add 1, divide by the result. So when we add 1 to the power of -2. And I guess it would be U to the -1 divided by -1.
Differentiate that.
Yeah. Hey, at least you don't have to take it early.
Yeah, right. Take it away. I remember that, taking it early stuff.
Do you know how much the multiple choice are going to be worth?
I think they were just like 1 point.
and they could be anywhere from chapter 6 to chapter 12.
Yeah,
So, okay.
yeah.
Yeah, whatever. Is it worth it to go over as far as like the multiple choice? Like, would you potentially reuse? Well, I mean, you're gonna just say yes. I mean, I was gonna say maybe multiple choice from prior exams, or I'm just trying to like.
Yeah, I probably wouldn't reuse. So they'll be fresh.
That set up and evaluate integral to find area between two curves. Remember what section that was?
Oh, 6.2, yeah.
6.2. Did you write that on?
I believe I did.
Okay.
That was the one I
Yeah.
actually remembered where it came from. Yeah.
The determine if it converges or diverges, is that going to be just any number of tests?
Yeah.
Okay.
Should I think if you look over a prior exam, it should be obvious which test you should use. Like factorials and stuff like that.
Okay. I mean, factorials definitely kind of spell it out
Yeah.
a little bit more than other stuff.
And there's
To the
you know,
power of H kind of spells it out. a
Yeah.
little bit.
Yeah, and I think, you know, for by and large, even if you didn't know, the ratio test is pretty easy to use in a lot of instances. Sometimes people try to use the root test and it doesn't really, it applies, but it doesn't simplify stuff. So, you know, I don't even know if it's worth mentioning, but like a thing I saw on the third exam was, I don't know what was going on in the bottom, but it was something to the effect of this to like a power of I don't know. What ended up happening is people were basically saying that the kth root of like a sum or a difference simplified to the kth root of each one, added or subtracted together, and that's never true. So. Unless they're both 0, I guess. So, you know, like algebra, right?
Mm.
Yeah.
Do you need the limit comparison test?
Limit comparison? Do you have a specific series in mind, or does it matter?
If you need it on the exam, something that would be close to that. And if
Yeah.
we don't, then we won't go.
And you know, without looking at the exam, I 100% honestly can't tell you what I put on the exam. A lot of stuff's happened since then, so.
Oh, so you made the exam like before break?
Yeah.
Oh.
Well, during break, but. Yeah, I don't have one. Somebody was asking me about this one on their old exam, exam 3. So I don't know what exactly it was, but it was like the sum from k equals 1 to infinity. Let's just say it's k squared plus k minus 3 over k to the 4th plus 3k cubed minus k squared plus 1. So this is kind of similar to one you had on your exam, but I'm blanking for another example right now.
I remember that because I got points there.
Okay. See, you learn from what you missed. It's not all bad. The idea of the limit comparison test, capital L, I don't know, k or n, whatever, goes to infinity, a sub k over b sub k. And the conditions there were, depending on what L was, what the limit was, and what the chosen series b sub k did, that's how we made an inference or conclusion about the given series. So we said, you know, try to pick something that's comparable. What's comparable to this as far as the b sub k goes would be a 1 over k squared. And other things are comparable, right? You got to know like the series that you're choosing to compare to, whether it's directly or by a limit. You got to know if it converges or diverges. So we could certainly compare this to 1 over k cubed as well. Might get a different result. Convergent p series with p larger than 1. So we know the chosen series converges. Now we compute the limit. At infinity. All of this stuff divided by our chosen series. Or times the reciprocal of our chosen series. So then what that gives us up top is a k to the 4th and some other stuff. On bottom, k to the 4th and some other stuff. We really don't care about that other stuff because we're out at infinity. So that's equivalent to the limit at infinity. Leading term up top, leading term on the bottom. And that gives us a limit of 1. So what that says is, in terms of this limit right here, if the limit at infinity of a over b is 1, it says that they're growing at comparable rates. Since it's 1, particularly they're growing, I shouldn't say that. They're growing at comparable rates. And this series converges. So since this series converges, and the limit is finite, not equal to 0, then both of those series do the same thing. That's our conclusion. You don't really think about it in terms of growth rates. You just say, okay, the limit's finite, it's not 0. Remember, if it's 0, you've got a separate condition. But any finite number means that this chosen series and the given series do the same thing. Since our series b sub k converges, so does the given series.
And if it's infinite, that means like they don't grow at the same rates.
Right.
Does that mean it diverges?
Not necessarily. So then the condition where the limit in the limit comparison test comes out to be infinite. So if L is infinite and the series that you chose for b sub k diverges, then the given series diverges. If the limit is infinity and b sub k converges, then it's inconclusive. You'd have to either choose a different b or a different test at that point.
You said if it's infinity and the other series converges.
Yeah, if you've got an infinite limit there and the b sub k was convergent, then it's inconclusive. So it has to be this and this. The other condition, when it was 0, is kind of similar to this condition, but if the limit is 0 and b sub k converges, then the given series converges. If both conditions aren't satisfied at the limit 0, let's say, and b diverges, then that tells you nothing. If it's a finite non-zero number, then both series do the same thing for the limit comparison. And honestly, if you're using a comparison test, I don't know, probably 95% of the time, if not more, it's easier to use a limit comparison because you don't have to establish which function or which series is larger than the other, which would be a very, very difficult thing to do with something like that. Is k squared smaller or larger than all of that other stuff?
You mean like I did on the test?
Yeah, right, like, well, so a lot of people did that, they're just like, this is less than this, so, and this one converges, so this one converges, and it's like, well, kind of like just covering up the elephant in the room, right? How did you know? So the limit, in my opinion, the limit comparison is preferable over the direct comparison. I think the only other times where it really makes sense with direct comparison is when you have these types of series, you know, where it would be really clear, if I compare that to this, it's really clear which one's larger and which one's smaller. If to you it's not clear which one's larger and smaller, then don't use the direct comparison test, use the limit. Because I mean, with the limit comparison test, we don't even have to compare another geometric to this geometric. I could choose this to be a P series and compare with this if I wanted to, and apply the limit.
So you said with the limit comparison test, if it goes to 0, then it's got a separate condition.
Yeah.
What do you mean by that?
So like, the condition on the limit is if it's a finite non-zero number, then both of those series will do the same thing, converge or diverge. But if the limit is 0, the chosen series that you're comparing to has to converge in order for that to imply convergence.
Well, so that could be like the same with the infinity, like what you're writing down now. Like if the bottom function like diverges and goes to infinity, then the top function diverges.
Exactly.
Or-
Yep. Yeah, and you know, I think the way that makes sense to think about that is if you take the limit at infinity and the limit is infinity, what that tells us as far as growth rates of those two things is that this A is growing much more rapidly than B. But if A is growing much more rapidly than B, and we know that B diverges, you know, A has to diverge as well. If the limit is 0, then we know that B is growing much more rapidly. And if we know B grows more rapidly, then A has to converge as well, because B is growing more rapidly, and B is a convergence series. This thing has to converge. If that makes sense. Out of time. I'm gonna get home to my wife. It's her 40th birthday today, so spend some time with her.